Welcome to Math 201. Today's lesson is on 4.2 global extrema. Note that the word global and the word absolute mean the same thing, so they will be used interchangeably throughout the lesson. A global extremum is the highest or the lowest point of a graph on a given domain. Finding global extrema on a closed interval from A to B is a three-step process. Okay, so global extrema will always occur at a critical point or an endpoint of the closed interval. So to find global extrema, you want to find the critical points, plug the critical points and the endpoints into the original function, choose the highest and lowest y values. So let's think about why this works. Okay, so I have a closed interval. We'll just say A to B. And we have a continuous function. Um, so it's gonna like do some stuff like that. Okay. And then the very highest point and the very lowest point have to occur either at a critical value, a critical point where the derivative is 0, or an endpoint. Okay, so in this case, the highest point was at a critical point and the lowest point is at an endpoint. Okay. So the way you identify the global extremum is to find all the critical points and the endpoints, plug them into the function. The biggest y value will be your global max, and the smallest y value will be your global min. Let's try it out. Find the global extrema for f of x equals 2x cubed minus 3x squared minus 72x plus 5 on the interval from -2 to 6. So we start by finding the derivative because we start with critical points. We start by finding critical points. So I have 6x squared minus 6x minus 72 equals 0. I can solve this factoring out a 6. And then divide that 6 out. And the x squared minus x minus 12 factors to x minus 4, x plus 3. And so I have two critical values, -3 and 4. Um, I am interested in the interval from -2 to 6. -3 is not in that interval, so I don't care about this. It's not in the interval from -2 to 6, so I don't care about it. What I want to look at is a table of values, x, y, where y is the original f of x. And I want to put in critical values and endpoints. So critical value of 4, I'm not going to put in the critical value of -3 because it's not in the interval I'm interested in. And then I'm going to put in my two endpoints, -2 and 6. And then plug in. Just want to get y values for each of these x values. So let's see, f of 4 would be 2 times 4 cubed minus 3 times 4 squared minus 72 times 4 plus 5. So that comes out to -203. And then f of -2, -2 cubed is -8 times 2 is -16. -2 squared is 4 times -3 is -12. -2 times 72 is 144. And then plus 5, and that comes out to 121. And f of 6, I'll just tell you, use a you don't have to use a calculator, you can figure this out in your head, but I'll just tell you it comes out to -103. And then I just picked the highest and lowest y value, and those are my global max, my global min. So this one is the lowest, and this one is the highest. So I'm going to write my final answer in a different color here. So I say there is a global minimum value of negative 203 at x equals 4. And we say there's a global maximum value of 121 at x equals negative 2. Okay, we've reached our first activity for the lesson. Pause the video, try the problems, press play when you're ready to go over it. Consider the function g of t equals t cubed minus 3t squared plus 20 on the closed interval t from negative 2 to positive 3. Find the critical points. So critical points, take the derivative, set it equal to 0. So that would be 3t squared minus 6t. We set that equal to 0. Factor out a 3t, and I'm left with t minus 2. So I have two critical points, 0 and 2. Those two critical points are both in the interval I'm interested in. So I'm going to consider both of them. List all the values of t where g of t could have a global maximum or a global minimum. It could be at one of the critical points I just found, or it could be at the endpoints of my interval. So the critical values we just found were 0 and 2. The endpoints of the interval are negative 2 and 3. So there are 4 t values where we could have a global max or a global min. And the way I figure it out is I get y values for the original function g. So I'm going to do t and g of t. Remember, g of t is the function t cubed minus 3t squared plus 20. Okay, and I'm going to plug in these 4 t values where I could possibly have a global max or a min. Okay, so if I plug a negative 2 in here, I get negative 8 minus 12 plus 20 is 0. If I plug a 0 in here, I get 20. If I put a 2 in for all my t's, I get 8 minus 12, which is negative 4, plus 20 is 16. And if I plug in a 3, I get 27 minus 27 plus 20, which is 20. So I have actually a tie for the largest y value. It's 20. And my 0 is my min. And then I have my max is 20. So let's write this out as a sentence. We would say G has a global minimum value of 0 at t equals negative 2. And G has a global maximum value of 20. And it happens at two different x values. So we would say at x equals 0 and x equals 3. Okay, so now we can also find sometimes global extrema on an open interval. We can't plug the endpoints in because the endpoints aren't part of the interval, but we can think about what happens near them. Okay, so still have a 3-step process. Find the critical points, classify each critical point as a max, a min, or neither, and then determine the end behavior to see if a max or min is possible. So for example, I have a polynomial function, f of x equals 3x to the fourth plus 4x cubed minus 24x squared minus 48x. So I want to find global extrema, the global max and the global min. I'm going to think about the end behavior before I do anything. Okay, so the end behavior, which is the behavior towards the ends of the interval, so near negative infinity and infinity. This is a polynomial function that has a positive leading coefficient and an even degree. So that means its end behavior is both arms up. Okay. Sort of no idea what happens in the middle. Could have all kinds of stuff going on there. They could go really high or really low, but these go up forever. Okay. So that means I can have, there's no possibility of a global maximum, right? If the arms go up forever on both ends, there is no global maximum possible because it just keeps getting bigger. Okay. But I could try to find a global minimum. So I want to look for critical points and um, classify them and see if I can find a global min. So critical points happen when f prime of x, which is 12x cubed plus 12x minus 12x squared minus 48x minus 48. Where does that equal 0? Okay, this is a little bit tricky. I am going to factor by grouping. This is a technique that we don't see that often. Okay, so I'm just going to group my terms because what I noticed is I was like, oh, these both have a 12 and these two both have a 48. So I could factor a 12 out here and a 48 out here, and maybe I can do factor by grouping. So for this first parentheses here, this isn't multiplication. I'm just grouping these. In fact, to make that a little bit clearer, let's write this as plus negative 48. Okay, there we go. So in my first set of parentheses here, I can factor out a 12x squared. So I'm going to have 12x squared times x plus 1. Okay, and then in the second set of parentheses, I can factor out a negative 48. Negative 48 times x plus 1. And now that I have factored each of these parentheses, I have a new common factor has emerged, x plus 1. So I'm going to factor out that x plus 1. And what's left is 12x squared minus 48. Set each factor equal to 0. So either x plus 1 equals 0 or 12x squared minus 48 equals 0. And here I get x is negative 1. And here I get x squared is 4, which means x is plus or minus 2. So I have 3 critical points. And I need to determine which one's the lowest. So I'm just going to make an XY chart. And I'm going to put in just the 3 critical values, -2, -1, and 2. And I'm plugging into the original function, because I want to know the y values when I'm graphing this thing. If I was actually looking at a graph of this, what I'm looking for is the lowest y value on the graph. They could only happen at a critical value. So I'm plugging in these values in here. I'm just going to, for the sake of time, tell you what these come out to. You can put them in a calculator. We get 16, 23, and negative 112. This is my lowest y value, negative 112. So we say that f has a global minimum value of negative 112 at x equals 2. Okay, at this point, you should pause the video, take a few minutes to work through this next activity, and when you're ready to go over it, press play. Consider the function g of x equals 3 halves x to the fourth plus 4x cubed minus 3x squared minus 12x on the whole real line, negative infinity to infinity. We're going to start by finding all the critical points. So critical points are found by taking G prime and setting it equal to 0. So that is going to give me 6x cubed plus 12x squared minus 6x minus 12. Set that equal to 0. And we have another situation where we're going to have to factor by grouping. Um, I'm going to put parentheses here, group those together. And I recognize I want to group those because um, I can pull out a 6x squared from both of them. And then these two, I could pull out a negative 6. So looking at this first set of parentheses here, I'm going to have 6x squared. And what's left is x plus 2. And then when I look at my second two terms, I can factor out a negative 6. And what's left is x plus 2. And once I have grouped my terms and factored each of the groups, I have a new greatest common factor, a new common factor that can be pulled out, the x plus 2. So I've got x plus 2 times 6x squared minus 6. We set that equal to 0 and solve it. So either x plus 2 equals 0 and we get x equals negative 2, or 6x squared minus 6 equals 0 and we get x squared is 1, or x is plus or minus 1. So 3 critical points. Classify the critical points as local maxima, local minima, or neither, using any of the techniques from chapter 4. I'm going to use a number line, the first derivative test. So I'm going to put a nice big number line here. I'm going to put all the critical points on there. We've got negative 2, negative 1, and 1. Put some fences at each critical point. Those are the places where G prime equals 0. Now I want to know, where is G prime positive and where is it negative? The best way to figure that out is to look at the factors of G prime. Those factors are x plus 2 and 6x squared minus 6. Now I want to look at the value of each of these factors in each of these 4 intervals. So for x plus 2, if I plug in something less than negative 2, like negative 10 plus 2 is negative 8, which is a negative number. Plug in something between negative 2 and negative 1, and like negative 1.5. Negative 1.5 plus 2 is positive a half, which is a positive number. And then pick a number between negative 1 and 1, like 0. 0 plus 2 is positive. And then plug in a number bigger than 1, like 10. 10 plus 2 is positive 12. And then we repeat for the factor 6x squared minus 6. Pick a number smaller than negative 2, like negative 10. Negative 10 squared is 100, times 6 is 600. 600 minus 6 is definitely a positive number. And then we do the same thing for a number between negative 2 and negative 1, like negative 1.5. So negative 1.5 squared is 2.25. 2.25 times 6 is bigger than 12, and 12 minus 6 is positive. So something bigger than 12 minus 6 will definitely be positive. Even if I don't know exactly what it is, I can tell it's going to be positive. And then a number between negative 1 and 1, like 0. If I put a 0 in here for x, I get negative 6, which is negative. And then put in something bigger than 1, like 10. And we get 600 minus 6, which is positive. So now I know the sign of each factor of f prime, which means I can figure out the sign of f prime itself by multiplying. So a negative times a positive is a negative. Then positive times positive is a positive. Positive times negative is negative. And positive times positive is positive. And now that I know that the signs of f prime are, I can figure out the behavior of f in terms of whether it's increasing or decreasing. Remember, F prime negative means F is decreasing. F prime positive means F is increasing. So we've got decreasing, increasing, decreasing, increasing, which means we've got a min and then a max and then a min. Okay, are any of the critical points you found global maxima or minima? So I have found some local maxima and minima using my sign chart. But in terms of global, remember I'm looking on the whole real number line from negative infinity to infinity. And my function was g of x equals 3 halves x to the fourth plus 4x cubed minus 3x squared minus 12x. And this is a polynomial that has a positive leading coefficient and an even degree, which means both arms up for n behavior. Okay, so there's no global maximum. Okay, even if there's a really high bump in here, it's not the highest point because these arms just go up forever. Okay, so we can't have a global maximum, but there are two local mins. We did find two local mins. And they happened at x equals -2 and x equals 1. So whichever one has the smaller y value is the global min. So we just make a little chart. T, oh, these are x's, sorry. X and g of x. I'm going to put in -2 and we're going to put in 1 and we're plugging into the original function g. So if I put in a -2, I get 4. And if I put in a 1, I get -9.5, which means that this one is my global min, the smaller y value. So G has a global minimum value of -9.5 at x equals 1. Number 2, consider the function h of x equals x squared over 4 minus x squared on the open interval from -2 to 2. Let's find all critical points um, as a first step. So critical points happen when the derivative is 0 or undefined. So let's start by taking the derivative. Okay, this is not just a polynomial. We're going to have to use the quotient rule to figure this out. So we're going to have f prime g. So that would be 2x times 4 minus x squared. That's f prime g minus f g prime all over g squared. And I want to know where this function is undefined and where it's 0. So h prime of x is undefined when the denominator is 0. And that happens when x is positive or -2. Um, we can ignore these because they're not in the interval I'm interested in. Okay, so I'm only interested on the open interval -2 to 2. I don't care what happens at -2 and what happens at 2. So I can ignore these. Okay, and then the other place that I have critical points is when h prime equals 0. So h prime of x equals 0 when the numerator is 0. The only way a fraction can equal 0 is if its numerator is 0. So I'm going to set the numerator equal to 0. Okay, so I get 8x minus 2x cubed plus 2x cubed equals 0. My 2x cubes cancel. Oop, that one was supposed to be plus. 8x equals 0, that happens when x equals 0. So I have one critical point at x equals 0. Next, I want to classify the one critical point I found. I want to classify it as a local max, a local min, or neither. So I'm going to make a sign chart, put the critical point on it of 0, and then I want to look at the derivative h prime of x, okay, which was 8x over 4 minus x squared squared. Okay, so h is a quotient. I'm going to look at the numerator and the denominator separately. So let's look at 8x and then 4 minus x squared squared. So 8x is going to be negative when x is less than 0 and positive when x is bigger than 0. And 4 minus x squared squared is always going to be positive because whatever this value comes out to, we're going to square it and you're going to get a positive number. So h prime, which is a negative divided by a positive, is negative here. And in the next interval from 0 to infinity, it's a positive divided by a positive, which is a positive. Okay, so that means that h goes from decreasing to increasing, which means 0 is a min, a local min. Are any of the critical points you found global maxima or minima? Explain your reasoning. So I have a local min, so a valley in its neighborhood, but I have to know what happens near the ends of the interval, near plus and minus 2. So h of x, which was x squared over 4 minus x squared, what does it look like? What is its behavior near x equals positive and negative 2, the ends of the interval that I'm interested in? So I'm going to look at the limit as x approaches 2 of x squared over 4 minus x squared. And my numerator is going to go to 4. My denominator is going to go to 0. Okay, so this is going to 4. This is going to 0. So I have numerator going to 4. The denominator isn't 0. It's getting smaller and smaller and smaller. So I'm having like 4 divided by 0.1, divided by 0.01, divided by 0.001. And when you divide by a really small number, the value of the fraction goes to infinity. And this actually happens if I'm taking the limit as towards negative 2 as well, because this is squared and this is squared. So this is the same for positive and negative 2. Okay, so let's see, what is h of 0? 0 was our only critical point. If I plug a 0 in here, I get 0 over 4, which is 0. So if I try to just sketch what I know about this graph of h, I know it has the point 0, 0 on it. And I know that at 2 and at negative 2, the graph goes up to infinity. Okay, the y values are going to, the limit is infinity. So it's going to do something like go up like that. So these are like asymptotes. And the graph like does this. Okay, so because I know the end behavior, I know the behavior near the end points is going towards infinity. I know that this local min has to be a global min. So h has no global max because it goes up forever. And h has a global min value of 0 at x equals 0.